All right, so today we're going to continue, probably conclude with list-based or lists. That is array-based lists, which we're done with, and then linked lists. And we're going to continue from where we left off last time. We were in the middle of designing this linked list. Remember that a linked list basically it does not hold elements in an array. Instead, each element is held in a node, and those nodes are linked together through references. Each node has a reference to the next node, the next node, the next node. You have the head of the list, and then you have the tail of the list. Each node is placed in a chain, and that's why we call them linking together. And basic operations now involve, instead of random access where you can jump to a particular index value, you now have to traverse the entire list to get where you're going. Remember that we are online, so if you have any questions, go ahead and post to Piazza or to YouTube if you have any. But otherwise, that's where we'll pick it up from last time here. Remember that we showed this demonstration here where it's better to keep track of the size than it is to have to recompute the size every single time. So let's go ahead and restore that size. All right, I'll take out that to-do variable right there. All right, oops. Restore this. All right. So initially when we create the linked list, the size will be 0. And whenever we add something, say to the head, then we need to increment that, that value. Otherwise, now we don't need to compute the value. All we need to do is return this dot size. Right? Now, if we ever take anything out, we'll need to, of course, make sure to decrement that variable. If we have any other add methods, then we'll need to make sure to take care of that there as well. Right? So actually, let's do that next. Let's go ahead and create another add method where it's going to be public void add element at index. Right? T, and there's the element. And then we'll have an int index. Right? Now, remember that this is not an array-based list, so we don't have an array that we can index, but we can still talk about the list in terms of indices, right? If you have 5 elements in there, 10, 20, 30, 40, 50, and you want to insert 42, say, at index 0, that means that, well, with the array-based list, that means that we shifted everything down and put 42 right here. If you wanted to insert it at index 1, that means that you shifted these 4 things down to make room for it, right? So it still makes sense to talk about things in terms of indices. Let's first make sure that with the indices are, that the index that we're given here makes sense. So if the index is less than 0, right, or the index is greater than size, this dot size, right, then we'll go ahead and throw an exception here. Throw new runtime exception, right, index out of bounds. Right, and then we'll just simply go ahead and have index here. Now, why did I go strictly greater than the size? Remember, if there are 5 things in there, right, you can insert something at 0, 1, 2, 3, or 4. But can you insert something at 5? Sure. I mean, what does that mean? Right? 0, 1, 2, 3, 4, and then you insert it at index 5. Right? You're just inserting it at the end. Okay? So, if it's equal, then we should allow that. And only if it's strictly greater than the size are we going to not allow that. Right? In fact, we could go ahead and see what that looks like. If we wanted to insert it at, instead of the head, insert it at the tail end, right? I like that. Let's go ahead and implement that one first, okay? Add element to the tail. Well, do I have access to the tail immediately? Nope. What do I need to do? I need to go through the list, find the tail, the current tail, add a new element at the end of it, right? Visually, what would that look like? If I want to, come on, paste. Oops. Oh, wow, that's cool. I copied that stuff, and somehow it knew to do that. I didn't know that the GoodNotes supported that. Okay, excellent. Good to know. Come on, copy that, and paste. There we go. And paste. And suppose that the elements that are in there are, say, 10, 30, and 25. Right? Just to emphasize that it's not necessarily a sorted linked list. It's just a linked list. Right? Now, to insert a new element at the end, right, we want to insert, say, 42 down here. What do we have to do? Step 1, create a new node with 42 in it. Right? Step 2, find the current tail. How am I going to do that? You start at the head. That's not it. That's not it. That's not it. There, that's it, right? That's the current tail. I will make that point to the new node over here, and then I don't need to worry about the new tails, what that's pointing to, because that's going to point to null. Okay? So that's the idea. 1, create a new node to hold x, dot, dot, dot. I'm just going to go ahead and steal this code from up here. I won't call it the new head. I'll just call it the new node. Right? Because it's not going to be the new node, new head. It's going to be the new tail. If we wanted to call it new tail, we could, I guess. Tail. There. 2, find the current tail. Dot, dot, dot. Okay. What's that going to look like? I need to set up a loop, right? Remember this toString method? It looks very similar to what we probably want. We set up a current node and we initialize it to head, right? And then while the current node is not null, right? While we've not fallen off the edge of the list, we're going to go to the next node, next node, next node, next node. The second that we break out of this loop, though, however, current will be null. So is current going to be the node that we want? If it's null? Nope. Okay. So let's adapt that loop, right? Node t current. I will set that equal to the current the current list's head, this dot head, right? And while current is not equal to null, I'll go ahead and say current is equal to current dot next. Right. Current, and I'll just go next, get next, I guess. Is it? Get next. There. Cancel. There. Okay. Now again, is this going to work? Right? I start at the head, and then I go until I've fallen off the edge of the list. What I'm doing here is I start here, and I go to the next, go to the next. Now the current here is not null. So what am I going to do? I'm going to go ahead and go to the next, which is null. I went too far. How do I know to stop before I've fallen off the edge of the list? I need a different condition here. When do I stop? When the current, say that this is the current right here, right? When it's pointing to null, right? When the current's next is null, right? Or when the current does not have a next. Does that sound familiar? We put into our node class here a hasNext function, right? So while the current has the a next, we just need to keep going. While current dot hasNext, go to the next. Right? The second that I break out of this while loop, guess what? Current is now the old tail. Right? So what do I need to do? Step 3, make the old tail, right? Tail, that is current, point to the new tail. Dot, dot, dot. Right? How? Current dot set next to new tail. And we're done, right? As far as the list is concerned, as far as the structure is concerned. Why don't we have to worry about that new node's next? Because it points to null. Right? An alternative here would have been to keep track of both the head and the tail, if you wanted to. Right? I'm not going to do that, though. Are we done with the actual list yet? This function? If I'm going to be adding something, what do I need to add? If I add something, and there were 5 things before, and I add something to the tail, how many things are there now? 6, so size plus plus. Let's test that before we go on. I'll keep the random just in case. Right, there we go. Done. Right. I'm starting out with an empty linked list. List.add element to the tail. 10, 20, 30, 40, 50. 20, 30, 40, 50. What would our expectation be here? What would it look? What should it look like if it's correct? So I add 10 to the end, then I add 20 to the end. 30, 40, 50. So 10, 20, 30, 40, 50. Right? It should look like a sorted linked list now, right? Look like it is not actually a sorted linked list. What happened? Add element to tail failed at line 28. So think about some corner cases here. Right? What if the list is empty? What is the head going to be? Nothing. In other words, null. Right? So you can create a new tail here. Current is equal to this head, meaning that the current will end up being null. Right? Here, in fact, I'll set a breakpoint right here. Let's do a debugger here. Right? So the new tail, that has 10, right? We're doing the first iteration here where we add 10 to the tail. And then if I keep going here, step, what about current? Current is now null. Can you call current.hasNext when current is null? Nope. So we end up with if I go one more step here, it'll end up being a null pointer exception. Right? There we go. hasNext. Okay. So go back to the drawing board over here. Right? Well, if the list is empty, is there any difference between add element to head and add element to the tail? No. So what's one trick that I could do here? If this list is empty, something that I already know works is adding an element to the head, right? So this dot add element to the head of x and return. Now how do I tell if the list is empty or not? This dot size is 0. But you know what? That seems like semantically that doesn't seem right. This dot size is equal to 0. I want to use plain old English here, or something closer to English. If this list is empty, that sounds like a nice convenience function to have. Public boolean is empty. Right? Return this dot size is equal to 0. That's how you know it's empty. Right? And then I can use that down here and outside the class. Right? If this list is empty, then go ahead and add the element to the head because it's the same as adding it to the tail. Test again. Yay, 10, 20, 30, 40, 50. Right? That was one corner case that was screwing it all up, and I'm convinced that it works now. Okay. Let's go back and do what we were doing before. Adding it to an arbitrary index. Except that we've got a couple of these corner cases already figured out too, don't we? What if the index is 0? Add it to the head. This dot add element to head x. There. What's another corner case? This dot size, if you want to add it to the end, this dot add element to the tail. Right? There. We've got two of those cases already taken care of, the extremal cases here, the corner cases, right? And both of those will take advantage of the fact that since you're using this size here, if it's an empty list, right, and you want to add it at index 0 and it's an empty list, adding it to the tail takes care of that because adding it to the tail ends up calling it adding it to the head, and that takes care of all cases, right? Okay. Now we only need to worry about adding it to an arbitrary internal index. Okay, let's come over here and figure that out. Go ahead and get rid of this, and paste one more. Huh. All right, fine. Wow, it's so smart. But it's hooked up with the rest of my stuff. Copy, paste that. All right, there we go. And it's not 25, it's 125. There we go. All right, so what are the indices here? This is index 0, 1, 2, and 3. Okay? So if adding it to 0, adding it to 4, those are corner cases that are already taken care of. What I want to do is I want to add a brand new node here. And I'll go ahead and say that it's 42. And I want to add it to, say, index 2, right? I want to put it right here. What would that involve? I want to add insert at index 2. Okay? So what would that involve? Well, first of all, what do I have to do? I have to find the 2 nodes involved right here, right? I want it to end up right here, so that I want 30 now to point over here, and I want 20, and I want this one to point to the old one, right? So again, what would that look like? Let me do a different color. There we go. I would now point this one to the new node, and I would point this one to the old node. Pull it tight, and it now has become a longer chain with that link inserted inside. Right? So do I actually need to find this node right here? Yeah, okay, but I also need to find this node right here. So in other words, to insert it at index 2, I need both this node and this node in order to change the references. Right? So, step 1. Step 1. Find the node at index index minus 1. Right? Step 2. Find the node at index, right? Then create a new node, right? And insert between the 2 nodes. Dot. All right. Step 1, find the node at index minus 1. Suggestions? Well, if I'm going to end up doing the exact same thing in step 2, but with a different index, what does that suggest to you? Maybe make a method to do it? So, public node of t, get node at int index. There we go. Now suppose that that's already done. For now, just to get it to compile, I'll return null here so that we can actually use this, right? That's on my wish list, right, to do, implement that. Because if I already had that, what I could do is say previous is equal to get node at index minus 1, right? And node of t next is equal to get node at index, right? And then I can, that's step 2, right? And then I can create a new node. We've already done that now several times. So node t current is equal to new node containing the element x. There we go. There's the creation of the new node. And now what I want is previous, then it goes to current, then goes to the next node. Right? That's what I want it to look like. So how do I go about doing that? Previous dot set next to current. And now how do I set current to point to the next? Current dot set next to next. So it all comes down to implementing that other function right now. Right? Before we do that though, do I really need 2 calls to it? If I get this node right here, and I want the next node right next to it, and there are a million nodes in there, say. It took me 1,000,000 traversals to get to this node. It will take me 1,000,001 traversals to get to this node, for a total of 2,000,001 traversals. Or what could I do if I have this node already? Just get the next, right? So don't do 2,000,001 traversals. Do 1,000,000 traversals, and then just go previous dot get next. Right? Much, much better. Okay. Before I forget, what else do I need to put in here? I'll definitely return, but I'll do that implicitly since it's a void function. If you add something, What do you need to do? This dot size plus plus. Right. Do I need to do that right here in this case? Nope, because that function does it for me. Do I need to do it in the other case? Nope, because that function does it for me. Okay. So it all comes down to this one right here. Get that node at that index. How can I do that? I'll start at the head, right? Node t current is equal to this dot head. Right? And that's going to be at index 0. If index is 1, then I need to go to the next. If it's 5, I need to go next, 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 next. Right? Well, I guess that would be for 4, right? 0, 1, 2, 3, 4, right? So, next, 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 next. How many times did I do next? 1, 2, 3, 4. So, that suggests what kind of loop here? A for loop. For int I equals 0, I is less than index, I plus plus. Current is equal to the current dot get next. Do I need to worry about indexing here? I called it from this function over here, in which case I already checked for all the indices. Right? So keep that in mind, though. Do I need to check for indices here as well? Valid indices, that is. Right? Think about that, and we'll come back to it. Okay? Otherwise, I'll return the current. There we go. Okay? Let's test it. See if it works. Get rid of the node class here. Go over to the demo. And let's test it for inserting it right there. Right? So right between 20 and 30. Okay? Print that out. So list dot add element at index. I'll add 42 to index, what did I say? 3? Oh, no, it would be 2 then, right? 0, 1, 2. So it would end up inserting it right here. I'm just doing that for visualization purposes here. Right, so 0, 1, 2. And so I should expect 10, 20, 42, 30, and the rest of it. Hey, looks like it works to me. What else should I test? Insert at the head. Make sure that that corner case that I already thought about works. Looks like it works to me. Insert it at the end. So 10, 20, 30, 40, 50. That'd be 5 elements, so 5. Right? Now 42 should be at the end. Okay. What else? 1. That might be considered a corner case because it's a corner case of the general case. Right? 4. I probably should have just done all of them, right? Written a loop to do it. Right? There. I'm convinced it works. Okay. But now let's go ahead and use that function that I just wrote. Node of t, foo is equal. This is an integer, right? Foo is equal to list dot get node at index 3, say. Does that seem right? Now remember, I'm not in the list anymore. I'm outside the list, right? Should I be able to get your node? Right, you're the list now. Should I be able to get a node in the chain? Right? I should be able to get things, right? I should be able to get a particular element. I want the 5th element, right? Oh, here you go. It's 42 or whatever, right? But should I be able to get the nodes? If I did, what could I do? Foo dot set next to null. What did I just do? I broke your list, right? This is a leaky abstraction. We've broken encapsulation by allowing the outside world, right, in this case the demo class here, access to the internal representation of our data structure. And not only that, but we've allowed it to break our data structure here. Back to the drawing board. Okay, well, that maybe doesn't make any sense. Unless it's private. Right? Now, it is totally, completely fine to use this function inside the class as a convenience function all over the place. But now we are prevented from doing so outside the class. Good encapsulation, no leaky abstraction here whatsoever. Okay? Not only that, but it makes my life easier for the rest of all of the functions that we're going to write. So far, we only have a way of putting stuff in. Adding something to the head, adding something to the tail, adding something to the index. Now let's actually write a function that you can return something. So public t get element at index. Int index. Because I wrote that convenience function, what can I now do? Get node at index, get the node at that index, and then simply just get the element and return it. It becomes a one-liner. Now remember I told you to keep in the back of your mind, should we be doing index checking elsewhere? Well, when our only call here was from another function that already did index checking, that was perfectly fine. But does that break things now that we're not doing index checking somewhere else? So list.getElement at index, I don't know, 3, right? Int x is equal to, and then let's print out x. Right. So what should it be? 0, 1, 2, 3. It should print out 40 at the end. Yeah, there. So it looks like it works to me. But do we have proper index checking now? -1. Is that correct? It doesn't even throw an exception, right? It doesn't make any sense. 10. This one will probably be a null pointer exception. Right? Why? Because we're going too far. We're falling off the edge of the list. Okay. So what should I do here? Index checking. Same thing here, but if it is greater than 5, you want 5, 0, 1, 2, 3, 4, so this should actually be -1, right? Let's test it, make sure. So when you ask for something that doesn't exist, it now should throw an exception, index out of bounds exception. If you ask for something, how big is it? 1, 2, 3, 4, 5, 6. So you can ask for the 5th one, that should work. That should be 42, right? Or 50, there we go. But if you go one more, then that should be an index out of bounds exception, 6. Right? And we gave the outside world a chance to rectify that, right? List.getSize. You have a getSize function. You can check, am I about to ask for something that I shouldn't ask for, right? Is it within bounds? So, continue. Basic CRUD. Create. We have a way to put stuff in. We have 3 ways of putting stuff in. Retrieve. We have one way of retrieving things by using an index, and then you can use a regular old for loop if you want to. Update. Well, that's just removing something and then replacing it, so forget about that for now. But what about that last one? Remove an element at maybe a particular index. Let's do that. Public void remove element at index. Element at index. Right. Int index. Guess what? Same exact bounds checking here. Right. In fact, if you're putting that once, twice, thrice, however many times, maybe you could have a private convenience function that checked for that stuff. Right. I'll go ahead and leave it like this, though. So remove an element at index. What would that look like? Let me go ahead and get rid of all of this stuff. And let's suppose that we wanted to remove, say, well, what about the head? What if I wanted to remove the head? That seems like a special case, right? Because the class itself is keeping track of the head. Okay. What if we wanted to remove this guy right here? What would that look like? Remove it, but do you want to lose the rest of your chain? Nope. So you should make sure that the old one points to the one that you want to delete. It's next. Okay. Similar for this one right here. What about this one? What if we were to delete the tail? What would that look like? I would have to point the second to last one. There's a word for that, penultimate. The second to last one, I would have to point that next into null. Right? Vocab word for the day. Right? Okay. All of those operations would involve first finding what? Find the node at that index. Again, we've made it nice and convenient here. Node t current is equal to get node at index. That's the one that we want to delete. Okay? So what I want to do is previous goes to current, goes to next. What I want to make it look like is I want to transform that so that previous then goes to next. Well, do I have previous in order to skip the current? Nope. Node T. How do I get the previous node right before current? Again, what do we want to do? Want to delete current. ... So I need the one right before it, right? Get node at index minus 1. Now, same question here. Do I need to call this twice? No. Instead, it's just going to be previous dot get next. All right. Excellent. Now, how do I make it look like that? Previous dot set next to next, but I don't have a next either, do I? Okay. Node t next is equal to current dot get next. If you want to do it like this. Otherwise, all I would do is say set the previous to the current dot get next. And then save a line of code right there. All right. If I'm deleting something, there were 5 things in there before, and I delete one of them. How many things are in there now? 4. So what do I need to do to account for that? This dot size minus minus. Oops, there we go. Okay. Come over here, and let's see if it works. First of all, let's look at our list and see what we can delete. Let's go ahead and delete 30. That'd be 0, 1, 2. Right? So list dot remove element at index 2. And 30 should be gone. Looks like it works. What other corner cases should I test here? 0. All right. I'll test that next. What's the other one? The size, and that's going to be, in this case, 0, 1, 2, 3, 4, 5. That last element. Oops. 5. There we go. So I should have, I should be getting rid of 50 at the end here. Okay, that works. Now the last one, 0. Is it going to work or not? Well, it worked. In what sense? It ended up deleting 20. It didn't result in an exception, right? It ended up deleting 20 instead. Well, that's what would happen if I deleted 1, right? There. It ends up deleting 20. That's what I want. But it ends up deleting 20 if it's 0 as well. Let's walk through that. Get rid of this breakpoint. Add in this breakpoint. And continue. All right? Get rid of that breakpoint. Sorry. And continue. There we go. So remove element at index. I'm going to step into that. Right? At index 0. Is this going to throw an exception? No, because again, index is 0, so it gets by this check right here. Right? Previous is equal to get node at index 0 minus 1. What's that going to look like? So 0 minus 1, that's going to end up being, I want the node at index -1. Does that make any sense? Nope. But when we step into it, it does make sense with respect to this function right here. Get node at index. Well, remember, index is what again? -1. Right? So when I step over this, I initialize it to the head. This for loop doesn't execute at all. and then we simply return it current, which is going to be the head. Right? At this point, you can see that the previous, if I go to the next right here, that is going to end up being 10. So we end up deleting the previous is next, which is 20. That's why it was deleting 20. All right. Maybe we need to treat that as a corner case. All right. If the index is equal to 0, then I will want to remove the head element. ... Class dot. It would be really nice if somebody wrote that function for me, right? If you've got a wish, grant your own wish. Right? This dot remove element from head. There we go. And then return. Because we don't want to do the rest of this stuff here. Okay? It'd be really nice if we had that function, right? Well, okay, let's make it. Public void remove element from head. What would it look like? Again, visually. Here's the old head. Right? How do I get rid of this guy right here? I need to make sure that the old head points to now the next one. So this dot head is equal to this dot head dot get next. And you're done. Return implicitly or explicitly if you want to. Right. Let's test it again. Go out of debug perspective there. And there. Did it delete 10 properly? Yep. All right. All good. We've got plenty of time. What about some other convenience things? For example, clear. Public void clear. In other words, what will the behavior of this be? It removes all elements from this list. It clears it out. How would I do that? This dot head, set it to null. What else should I set though? Be careful. Say again? This dot size is equal to 0. In fact, that reminds me, is that all we needed to do? This dot size minus minus. Okay. Let's find out. List dot clear, right, and then print it again. I'm not sure what it prints for an empty list. Size is 0, and then yeah, it's nothing there. Okay. All right. What else? What would you want if you went shopping for a list data structure? If you went shopping for a linked list data structures, what would you want? Contains? Okay, a search method. Public Boolean contains, and then an element of type X. Okay. We did this before when we did the integer-based array list, right? Or the array-based integer list. And we were able to do that because here's an integer, here's an integer. How do you tell if they're equal? Equals equals. Here we've got an integer. Sometimes, yes. We've got elements of type t. Given two elements of type t, right? T sub x and t sub y. How can you tell if x is equal to y? Is that the proper way of doing it? Would that work for strings? No. Right? So think about that while we're writing this. First of all, I want a linear search kind of algorithm here. Right? Let's go ahead and go with a traditional for loop. For int I equals 0, I is less than this dot size, I plus plus, right? And what I'll do is I'll get the node at index I. Node is equal to, actually, sometimes, usually when we say nodes, we use like U, V, or W, right? Y, I don't know, just because like A, B, C are coefficients, X, Y, Z are Cartesian coordinates, right? Alpha, beta, pi, we don't want to write those out, right? So we just use U or whatever. I'll use U here. Is equal to this dot get node at index I. And then I can check for that element. If u.getElement, that gives me an element of type t. And remember, we already said that we can't do this. If that's equal to the thing that we're looking for, then I'll return true. All right? Otherwise, after I've got done with it, return false. There we go. Again, we already said that this is not going to work. Equals equals. Okay. I will demonstrate that over here. Can I do random strings? r.next string? Nope. Next. All right, fine. That's not that sophisticated. Oh, I've already cleared it. I don't want to clear it. Let's search for 42. If list.contains 42, it'll probably end up working here because these are integers, and it'll do unboxing, and then, oh, that integer is equal to that integer, right? System.out.println, yes. Right? Else, just to make sure that it actually works, we'll output no. No. There we go. And so, yes, it does find 42, but that's because they're integers and equals equals works for integers. What if I did, say, 10, bear with me while I type it all, 20, 30, 40, that's how you spell 40, right? 50, there we go. And then I could have just made all these into, there, 42. Why is it not compiling, by the way? I created this list to hold integers, and then I put a bunch of strings into it. All I need to do is change that to strings, and it's perfectly fine here. Right? So now does it contain 42? It might even say yes here, because if it's a static string, yeah, okay. So string key is equal to new string 42. I'm just forcing it to create a brand new object here, and you'll see that does it contain that key, and it should end up saying no now. Right? But 42 is in that list, right? It's right there. 20, 30, 40, and then 42 as a string. Right? Why is it not working? Because that's not how you compare objects. How do you compare strings? Dot equals. Does it work for all objects? Yes. Why? Where's the dot equals method defined? In the object class. Because of inheritance, every single object will have a dot equals method. Now, whether or not it is a correct method, that's a question of whether or not they overrode that method in the subclass to correctly check for equality. Right? I wonder what the dot equals method looks like in the string class. Find equals. There we go. Well, it does use the equals equals first, because if they're the same thing in memory, they are definitely equal, right? Otherwise, it goes through a much more sophisticated checking here. A string Latin 1 dot equals. That's probably some sort of a loop there. There. What's it doing? It's going character by character by character, and same character, same character, same character, same character, and then it returns if they're all the same character. Right? And that's how that's working. So now it will report back yes, because 42, the character 42, matches the character 42. Yes, it is in there. Right. Okay. All right. Is that a good implementation? Let's find out. Right. So what I want to do now is I want to insert a lot of elements. List for int I equals 0, I is less than n, I plus plus. I haven't defined n yet here. We'll do it in a second. List.add actually no, let's go ahead and add at head I. So I'm going to add elements 0, 1, 2, 3, 4, 5, up to whatever n is here. Int n, I'll make sure that it's small to begin with. Add element at head, and I need to make this into an integer again. There we go. So I'm adding 1,000 elements to this list. Save. What's wrong? Add element to head. There we go. Done. Right? And I'm actually not going to print it out because I don't want 1,000 elements here. But you can imagine what it would look like. Right? What's going to be the first element? If I'm always adding it to the head and the last thing that I add is 999, it should be 999. 998 ... Okay. All right. Let's search for 0. Does it contain 0? Trust me, it does. I don't want to scroll over. Right? I'm not going to print it. Instead, I will say list.contains 0. Okay. True. It was at the very end. Okay. Let's follow the same pattern here, but instead of 1,000 elements, let's go with 10,000 elements. Still true. Right. 100,000 elements. Okay. It's taking a little longer. I don't know why. All right. I do know why. Do you know why? There, finally, true. All right. So that wasn't that bad. That was maybe like 5 seconds. I don't know how long I was talking there. But now let's go up to 1,000,000 elements. How long should I wait now? Probably 5 minutes or so. If I went up to 10 million, I'd be waiting for hours. If I went up to 100 million, I would be waiting for days. Right? Why? Contains. Say what? It's I can't. So sorry. It's a linear search, but not only that, it ends up actually being a quadratic search, which is not a thing, right? Nobody has a quadratic search. Why is it? Why is it end up being quadratic, right? Instead of n, it's going to be n squared, right? And again, this is kind of bookending and giving a preview on what we're going to be looking at with respect to algorithms and algorithm analysis. Do you remember the painter's paradox that we talked about? So in Computer Science 1. So there's this painter, and you pay him by the hour, and they've got this 100-foot long fence that you want to paint, right? And you leave, you come back 5 minutes, and oh wow, they've gotten a lot of work done, right? They've got the first 10 feet of the fence done. Great, this will be done. This is going to be really cheap. You leave, you come back an hour later, and they've only got the first 20 feet done, right? It only took them 5 minutes for the first 10 feet, but then it took them like an hour for the next 10 feet, right? You go, okay, well, maybe they just took the lunch break, right? You come back 4 hours later or something like that, and they've only gotten 30 feet done, right? This is going to cost me a lot of money. So they finally say, how are you painting this fence? Show me how you're painting, right? And so what do? They go to one end of the fence, dip their paintbrush, walk all the way back to where they're painting, paint, right? They run out of paint, walk all the way back to the beginning of the fence. In other words, they're going back and forth for every single paintbrush stroke or whatever, however much paint is in a paintbrush. Right? Is that the way to do it? Nope. What did he yell at him? Pick up the damn paint can and take it with you, right? So paint as you go along, right? Not walking back and forth. This is walking back and forth. Why? For each eye, start at the beginning. Remember what is get noted index? It starts at the head, traverses I until it gets there, right? All right, now get I plus 1. Start back at the beginning, walk back, walk all the way to 11, right? Start at the beginning, walk all the way to 12. Start at the beginning, walk all the way to 13. If you found a closed form solution of that, which we will eventually, you'll find that it's n squared. Right? So as we go up in orders of magnitude by 10, from 100,000 to 1,000,000, it's going to slow down by a factor of 100. Right? Why? Because 10 squared is 100. It's going to be 100 times slower. Nope, I'm not paying you. The painter, that is. Right? So what should I have done here instead of this naive for loop? maybe a while loop instead, right? While current, and I will need current here, node, whatever t, current, I'll start at the head, this dot head, right? And while the current is not equal to null, in other words, while we've not fallen off the edge of the list yet, that's where I will make my check. If current dot get element is equal to x, then return true. I've picked up my my paint can with me and have taken it with me. Instead of starting it all the way back at the beginning, right? I am taking the paint can with me, and I'm at the current one. I don't start at the beginning. I just go to the next, go to the next, go to the next. Right? And I can guarantee you that even at 1 million, this is going to execute in a blink of an eye. Well, not in a blink of an eye. I do have to put stuff in there, I guess. I saved it, right? Done A, done B. There we go. Oh, we'll know it's done. There, done A. Oh, what? Did I not? I saved it, right? I saved it, right? Oh, no. Now it's even worse. Now it's a infinite loop, right? It's not going to take hours now. It's going to take forever. Why? What did I not do? Current is equal to current. Yes, thank you. Yes, I did. Football junkie, whoever you are. Get next. YouTubers. Right. There we go. Blink of an eye, like I intended. Questions on this? No? Then let's talk about other variations, right? You can also have doubly linked lists, doubly linked lists, right? You can keep track of a next and a previous node, right? Previous, I'll spell it all out, previous, there we go. What would that look like? Bring my pad up here again. Right. There. Now you have a next reference and you also have a previous reference. Maybe you also keep track of both the head and the tail. So why would you want this variation? Well, you can traverse one way or you can traverse the other way. All those things that we were doing to, okay, well, I need to get this node and then I also need to get the next node and the next node. I need these 3 nodes just to find this one. Well, the way that we did that was by hackishly getting the one previous to it and then next. What you could do is just get this node, then you can work both ways, get the next and the previous. Right? And that's a doubly linked list. Right? You also have, I guess as one other variation, you could possibly keep track of both the head and tail elements. Right? Now there, it's going to be a little bit more complicated in that if you insert a new tail, you've got to update the new tail, just like if you insert a new head, you have to update the head. Right? What happens when you've got an empty list? They both are pointing to each other. They're both null. Okay. There's another variation called a circularly linked list. Circularly linked lists. Right. Instead of having a tail, right, the last element points back to the first. Right? So there's really no first or last. Right? That would look something like this. Right? You could still keep track of the head, or instead of calling it the head, what you could call it is, say, the current. And you always have this current element. Right? Sometimes it's this one, sometimes it's this one. Right? If you go to the end of the list, really there is no end of the list because you're just going to go ahead and circle back onto yourself. Right? It forms a circle, unless it's empty, in which case, I don't know, a dot or something. Right? And that allows you to go around. Maybe if it's a doubly linked, circularly linked list, you could traverse both clockwise and counterclockwise. This allows you to have some sort of a round-robin data structure. Has anybody ever heard of a token ring network? I'm getting further and further away from the years that anybody will remember LAN parties. People still have these LAN parties, but they don't use token ring networks. They bring their own routers and hook them all together, right? Using Cat5. Cat5, is it? That cable. It looks like a telephone cable, but it's fatter, right? That's Cat5. It used to be that you could have a token ring network, which would look much more like coax, and then you'd have to have computer. But to make sure that it was a ring, what did you have to do? Make sure that all the computers were in a circle, right? And then everybody got a slice of the network time, right? You can send data, now you can send data, now you can send data, and then it went back all the way to the beginning, a token ring network, right? And that kind of data structure would support that. There we go. What else? You can have unrolled linked lists. That's the last one I probably will mention, right? An unrolled linked list is where each node doesn't just hold necessarily one element. Instead, it can hold an array of elements. In other words, this is kind of like a hybrid. You don't have just linked lists and array-based lists. What happens when you combine them, right, into some sort of Frankenstein unrolled linked list? And it looks something like this, right? So each one of these things, each one of these rows, that's a node. But the node itself contains an array that you can hold multiple elements with. The head will point to that first node. That first node then needs to point to the second node, which again holds an array of elements. And you can imagine what this would look like. That once one node is full, then you have to create a new node at the end of it. Right? And then you can fine-tune this. You can fine-tune M to be a page size or whatever fits into memory in one page. And now then you can fine-tune it to reduce cache hits and misses. Right? So much more sophisticated ways of doing it. You can also have what's called a skip list. And for that, I don't have a picture, but a skip list, where it's a linked list, but there are express lanes. So we don't have any mass transit here in Nebraska, or really anywhere close. But go on to a major city that has a subway system, right? Now the subway system is going to have lots of stops, right? That's called the local. Right? If this car stops at every single location along the route, right, then you're getting to every single node. But lots of commuters, they don't want to stop at every single one, so they get on the express, right, where it doesn't stop at these 4 locations. Instead, it goes from this location to the 5th location. And then if your stop is in between 2 major stops, well, then you can go ahead and transfer from the express to the local, and then only have to stop a few times. And I can show you what it would look like. Just a Google image search here, skip list, right? And image. There. Something like this, where you've got express lanes. I think it kind of looks like a notes or music or something like that, right? But you've got this express lane where you can jump from the first element all the way to, well, the end. Or you can go from the first element to the 4th element here. There's the express. Otherwise, these down here, they're all the locals, right? You can hit everything along the way. That way you can possibly jump to the middle of the list, like you can with an array-based list. But then now it's just a little further away, jump to the middle of the list, and then get on the local and skip towards it. That's why it's called a skip list. You can skip certain elements. Right? Okay? All right. Then you can also have what are called restricted access data structures, which will be stacks and queues. Right? And we'll cover these in depth when we come back next week. Otherwise, any questions? Do you want to see any other cool things to do with this list before I check it in and be done with it? Yeah. Ooh, okay. Yeah, you got 15 minutes. All right. Okay. So how does somebody do a for each kind of, all right, let's go over here to demo and let's see how it would look, right? For each integer, and I'm going to kick it down to 10. There we go. For each integer x in the collection list. I want to system.out.println x. Right? If this were like an array list, or if this were even a linked list, I called it my linked list. Why? Because there's already a linked list implementation in Java, right? And it conforms to the list interface. But if this were a regular old linked list that is defined by Java, then you could do this really easily. Right? How does it achieve it? In fact, let's go ahead and go back. Let's go ahead and declare a linked list integer. Foo is equal to new linked list. Let's break that open and find out how it achieves it. And then we'll adapt it for our purposes. I actually just wanted to show you it up here. There we go. So it implements all these things. Oh, I guess it doesn't do it here. List would implement it. There we go. Extends collection. Collection then. There it is. It has to be iterable. If something is iterable, then you can put it into an enhanced for loop. So let me go ahead and copy that. Go back to our implementation and make it, should be implements. There you go. Okay, whoa. All right. So be it. Elements of type T. There. It is an interface. I don't know why it was extends. That was kind of weird. I'd have to dive into that a little bit more. But now, what does that interface do? I have to add these unimplemented methods in order to support this. Once I do that, then, yeah, sure, you can go ahead and use it over here in an enhanced for loop. Right? Now, the trouble is defining how that works. Okay? Let's go all the way, there we go, iterator. Right? So, to be iterable means that you have this function called iterator that returns an iterator. Right? An iterator is just simply something that you can ask for. Is there another value? Is there another value? Does it has next, has next, has next? Sounds very familiar. But also, give me the next, give me the next, give me the next. And so we'll go ahead and implement that right here. I will return a new iterator of type T. There we go. And I'm going to define it right here in line. Right? Now, what functions does that define? It defines two functions. Do you have another one? And give me that next one. Okay? It is parameterized here so that it will work on the same values, right? Types, integers, strings, whatever you're doing, as are being held in the class itself. Right? But now all we have to do is answer these two questions. Do you have another one? And if you do have that other one, please give it to me. As it is right now, it's just returning false. So this would actually still work. It's just that it's not going to print anything out, right? Because I immediately say, no, I don't have another one, right? So to do that, we need to keep track of the current one. Up here in all of our code, how did we keep track of the current node that we were at? By creating a variable called current. Right? Where did we start it out at? This dot head. Okay. Private. There we go. It's okay to make this private because nobody. It's okay not to make this private, I believe, because nobody will ever see this. It's not part of the interface anyway, so nobody is ever going to be able to see it. But I'll go ahead and make it private explicitly here. Not this dot head, because this is no longer the list. What is this now referring to? The iterator. Right? So not me, but that head up there. Right? And it knows about it. Why? Because I'm inside the class. This is getting dangerously close to a concept called a closure, right? That's used all over the place in functional programming languages. Don't worry about that, though. It just works, right? Okay. Has next. Well, if I've got a now again, don't consider this as being the head. This is just where I start. I have a current node. How do I know that that current node is valid? This you have another value if ... the current node is not null. Right? Yes, here it is. I have it ready to give it to you. Right? If you want it, go ahead and ask for it. That's the other method down there. Next. Right? So what would that look like? If now this dot current, right? Now this is referring to the iterator, so I can refer to the current using the this keyword. This is not equal to null. Right? Return. Yes, I do have another one. The one I'm holding in my hand right now. Current. Right? Okay. What about getting the next? This one right in my hand is the one that I want to give you. I want to return current. Return current. This dot current. That doesn't work. Why? That's a node. You want to return the thing stored in the node. So this dot current dot get element. Right? But be careful, right? Remember that I screwed up before by when I fixed it so that it was no longer a for loop. I put it into a while loop. We got stuck in an infinite loop. Why? Because we never went on to the next. And I'm not doing that here either. What I need to do is I need to set myself up for the next time somebody asks me for the next. Right? This dot current is equal to this dot current dot get next. But now the problem is if I go to the next one automatically, the one that was in my hand is gone. So what should I do? Save this off into a variable of type t. Right? T sub x is equal to the current node's element. Then move on to the next node so that next time you call this function, you are set yourself up for it. Then return x. Okay. Let's see if it works. Hopefully it works. What's in? I've got 10 elements in here, so it's 987654321, I think. So there we go. 987654321. True. And you can use it in an enhanced for loop. All I had to do was implement the iterable and figure out how iterable worked for this particular list. How would that work if this were an array-based list? Instead of nodes, I would keep track of an index. Int current index is equal to 0 to start out with. Has next. Return this dot current index is less than this dot size, or the list dot size. Right? How do I go to the next? This dot current index plus plus. Right? And then return the value that was previous. Very nice way of iterating over stuff. In fact, now that it's iterable, how could I refactor some of this code? Contains. Do I have to roll my own while loop anymore? Nope. Instead, I can go into an enhanced for loop. For t x in, not x because that's what I'm searching for, ty in the this, right? Because this is iterable, right? If y equals to x, then return true. Otherwise, there you go. Right? Much more compact code. Anytime that you have logic to iterate over a collection, maybe you could put it into an iterable and then reuse that logic. Right? You just have to make sure that that logic doesn't lead to hours, days, centuries of operations. Right? Like it did before when we were at 1 million. This should still work. Of course, I don't want to print a million things, but I'll let it go. There we go. Go ahead, print your million. Oh, okay. It didn't take long to print a million things. That only took 9 minutes. Any 6-minute questions? No? All right, then. I'll see you next week, and we'll talk about stacks and queues.